How does phosphorus form 5 or even 6 bonds like this in violation of the 8-electron rule? Put another way, what do the lines mean when we draw PCl5 like this? At one point, it was thought that phosphorus could perhaps employ higher energy d orbitals in bonding. Perhaps you've even heard people espouse this theory. Folks working in the main group chemistry soundly rejected this theory in about the 1980s and earlier. The d orbitals are too diffuse and too high in energy to be involved. Instead, it's believed that the 8-electron rule is always followed. No stable main group compounds have atoms exceeding 8 electrons on the atom. Instead, it is the 2-center 2-electron bond that is sometimes replaced. So what is the 3-center 4-electron bond? Let's describe it using both MO theory and hybridization theory. The simplest compound with a 3-center 4-electron bond is perhaps xenon difluoride, which is a linear molecule, so let's use that as our example. Here's the Lewis dot structure. While we're going to do the MO theory explanation, let's borrow a principle from hybridization theory to start off because it will make things a little easier, namely Bent's rule. It says that the bond to a more electronegative atom will have more p character. Every atom in xenon difluoride has 3 lone pairs, which can be thought of as bonds to a group with 0 electronegativity, which will use as much s character as possible. We will assume the bonds between xenon and fluorine are being made with pure p orbitals, which turns out to be an excellent assumption. Because there are 3 lone pairs on each atom, which will use up 3 of the 4 possible hybrids, that leaves us 1 pure p orbital on each atom to form our MOs. We'll end up with 3 MOs from 3 p orbitals, 1 on each atom. There will be a fully bonding MO where there are n-phase interactions between the xenon p orbital and the orbitals of both fluorines. Then there will be a non-bonding MO where the xenon's pure p orbital doesn't have the right symmetry to interact with the salx of the fluorines. Finally, at highest energy will be a fully antibonding MO. Into these MOs, we need to place 4 electrons. 2 can go into a bonding orbital, and 2 will go into the next highest energy non-bonding orbital. This gives 1 bonding interaction to localize across the 2 xenon-fluorine interactions. In other words, the bond order between each xenon-fluorine is 1/2. The hybridization theory picture of the bonding is quite simple. You can have a full xenon-fluorine bond to one side of the xenon cation and fluorine anion, then you can do the same to the other side. Still here, the bond order is 1/2 to each fluorine.